Hi everybody, welcome to 9.2 Series and Convergence. So this is the big kid stuff, all right? If you ever have questions, make sure you ask in class or come to office hours. So we're gonna get right into the definition, all right? So if we have a sequence A sub n, then this summation, when n goes from 1 to infinity, right? We're just adding up all of these terms in this sequence. This is called an infinite series, okay? So the way we would note it is S1, S2, S3, and what that represents is S1 is the sum of the first term. S2 is the sum of the first two terms. S3 is the sum of the first three terms. S sub n is the sum of the first n terms. If we take a look at this example where we let our sequence an be 1 over 2 to the n, then we can see what this looks like, what this series looks like. So a1 or s1 is just a1, so 1/2. S2 is the sum of the first two terms, so 1/2 plus 1/4, so we get 3/4. S3 is the sum of the first three terms, so 1/2, 1/4, 1/8, so we get 7/8. Then the sum of the first n terms is going to come out to be some formula. So after we kind of look at these three, you might be able to make a conclusion and figure out the formula for S sub n, okay? So in this case, it's 2 to the n minus 1 over 2 to the n. We'll get more practice with that later on. So we then need to talk about convergent and divergent series, okay? So for infinite series, right, so the sum of the terms of the sequence, the nth partial sum is given by S sub n equals a1 plus a2 plus a3 all the way to an. So that's kind of what we talked about up above. If the sequence of the partial sum converges to S, some value, then the series, the sum of all the terms from n to infinity. So the infinite series converges. The limit S is called the sum, okay? So in other words, right, S is equal to the sum of this infinite series, which is equal to the limit as n goes to infinity of this series, all right? If S sub n diverges, then the series diverges. Okay, so we're going to go through all of this. So if this diverges, the series diverges. Okay, so for example, if we have our sequence from up above, 1 over 2 to the n, okay, then to figure out whether or not this series converges, S sub n is equal to the sum of the terms of this sequence, right? Which is equal to the limit of that series. All right, and now remember, we came up with the formula for that S sub n up above, 2 to the n minus 1 over 2 to the n. So we're really taking the limit of this as n is going to infinity. So we can simplify this. 2 to the n over 2 to the n just goes to 1, and we're left with minus 1 over 2 to the n. Plugging in infinity, we get 1 minus 0, we get 1. So therefore, we can conclude that this series converges, it converges to 1, but that's not the important part. The more important part in this section and when we're talking about series is whether or not it converges or diverges. So it's more important to say it converges rather than it converges to 1. All right, we're now going to focus on our first type of series. So let's move on to the next page. Okay, this first example is a telescoping series. And in order to figure out what the formula for S sub n is, we're going to have to use partial fractions and work our way to getting that formula. Okay, so here we go. Let's zoom in. If we are finding the sum of this sequence, remember this represents A sub n, okay? So that's something we have to keep in mind. This represents A sub n, and we're adding up all those terms, okay? Well, I noticed that we can factor this. So it becomes 1 over n plus 3, n plus 1. So now we need to use our partial fractions, all right? So we set that up, multiply everything by n plus 1, n plus 3, all right? When n equals -1, we're able to get b to be 1/2. When n equals -3, a is -1/2. So now we can rewrite this sum in terms of those partial fractions, okay? So we have -1/2 over n plus 3 plus 1/2 over n plus 1. Well, I can bring a 1/2 out, okay, because every term is going to have that 1/2. So I can take 1/2 times that series, right, the sum of this sequence, of all these terms in these sequences. And I'm just going to rearrange it so it's my positive minus this guy. So 1 over n plus 1 minus 1 over n plus 3. Okay, so now what we need to do is we need to start adding up the terms, right, of this series. And we have to remember, eventually we're going to get to this part here where the sum of this series is equal to the sum of all of the terms in this sequence, which is equal to the limit as n approaches infinity of this series. Our goal here is to figure out what the formula of S sub n is so that we can then take the limit, okay? All right, so we've got to do a little bit of work here. And what we're going to do is we're just going to write out some of the terms, okay? So we're going to work on this part here, all right? So we're going to take the limit as n approaches infinity. I could move this 1/2 out front here, which is what I'm going to do in the next step. And now we're just going to write out our sequence, okay, or our series, I should say. So when n is 1, I'm going to plug it into here. We get 1/2 minus 1/4. When n is 2, plug in those 2 for n, and then we get 1/3 minus 1/5. Plus our next term, when n is 3, we get 1/4 minus 1/6. Plus our next term, when n is 4, we get 1/5 minus 1/7. Plus, when n is 5, we get 1/6 minus 1/8. If we keep going, I'm going to go until we get to n, okay? When we keep going, we get, when n is n minus 1, so the second to last term, we get 1 over n minus 1 over n plus 2. Then when n is n, meaning our last term, we get 1 over n plus 1 minus 1 over n plus 3, which makes sense, okay? All right, but now we need to notice some things, okay? We need to notice that, hey, these 1/4, those are going to cancel. The 1/5 are going to cancel. The 1/6 are going to cancel. This 1/7 is going to cancel over here. This 1/8 is going to cancel in here over here. This 1 over n is going to cancel with something prior to it. This 1 over n plus 1 is also going to cancel out with something prior to it. So what are we left with? Well, we're left with this 1/2, this 1/3, this -1 over n plus 2, and this -1 over n plus 3. So this is going to allow us to figure out, hey, these three things really represent S sub n, okay? Well, all of these combined represent S sub n, but we can really just clean it up to be these terms here, okay? All right, so really what we're doing is we're now taking the limit as n approaches infinity of our S sub n, okay? So now when we use direct substitution, all right, we get 1/2 times 1/2 plus 1/3 minus 1 over infinity plus 2 goes to 0, and 1 over infinity plus 3 also goes to 0. So we end up getting 5 over 12 is the sum of this series, okay? So our conclusion is this series converges, okay? That's the more important thing. It converges to 5 over 12, but more importantly, it converges, okay? Let's try one more telescoping series before we get into geometric, all right? Okay, so we're going to look over here to our next example. So again, you're looking at it and you're saying, well, how do I know if it's telescoping? Well, when I have something like this, all right, where we can use partial fractions to break it up. So here's my partial fractions work, all right? And we break it up as 1 over n plus 2, n plus 1. So equals a over n plus 2 plus b over n plus 1, multiplying through. If we let n equals -1, we're able to get b to be 1. If n equals -2, we're able to get a to be -1. So when we kind of rearrange things a little nicer, we get the series to be 1 over n plus 1, or the sum of 1 over n plus 1 minus 1 over n plus 2. So to figure out what this sum is, right, we need to take the limit of that series. Well, we don't know the formula for S sub n. That's what we're going to find by plugging in all these different n values and seeing what kind of pattern we notice. Okay, so we're going to go ahead now and plug in and figure out some terms. So when n equals 1, we get our first term, 1 minus 1/2. When n equals 2, we get 1/2 minus 1/3. When n equals 3, we get 1/3 minus 1/4. Continuing on, when we get n is equal to the second to last term, n minus 1, I should have a plus sign in between those. And then finally, when n equals n here. All right, so what do we notice? Well, here, the 1/2s are going to cancel. So the last term, the last term and the first, right? Those are all going to cancel as we continue on. So we're just left with 1 minus 1 over n plus 2. So that gives us our S sub n formula. So this right here is S sub n. So now we can take the limit as n goes to infinity. And when we do that, we're just going to be left with 1. So our conclusion is this series converges to 1. Okay, the sum of all of these terms in the sequence, right, converges to 1. Now we're going to look at a couple other series, okay? Our next focus is going to be geometric series. So I'm going to focus over here. Okay, so a geometric series is in this form, all right? It's the sum of a times r to the n. And these terms written out are going to look like this. But one thing we need to note is that sometimes finding that S sub n formula, like we did in that telescoping series, is not always easy to do. So we'd like to find if the series can converge or diverge based on that sequence only, that a sub n, okay? So let's just kind of take a look at a few different scenarios here. And again, these are dealing with geometric series, okay? So we'll talk about what a geometric series is. Well, again, it's in this form, a times r to the n. So in this case, this is our a is 1, our r is 5 over 4 to the n power. If we were to just write out the terms and start adding those, right? This represents a1 plus a2 plus a3 plus a4. If we were to plot n versus an, right, just our sequence, we're going to get a graph that looks like this, just plotting those a1, a1, a2, a3, etc. Okay? All right, well, what's happening here? Well, an, this is our sequence, it's just the list of those terms. If we were to take the limit of that sequence, we would get infinity, right? It continues to go, it is unbounded, right? So we would say that the sequence diverges, right? Okay, but what about the series? Well, since the sequence diverges, the series is going to diverge, all right? Well, let's just take a look at the graph of the S sub n, right? So again, this is the sum of the first term, the sum of the first two terms, the sum of the first three terms, so on and so forth. And you can see it's going to go on forever. So we can go ahead and say it's going to diverge. Okay, it goes on to infinity. All right, so our conclusion is if the limit of a sub n as n goes to infinity equals infinity, then the series diverges, okay? But what happens if we don't have that? So let's look at this second example, all right? This is a geometric series, 5 over 4 to the n. We could rewrite it as 5 times 1/4 to the n power. Writing out the terms and adding those, okay? This is A1, A2, A3. We could plot those, and what we should notice is our sequence is getting smaller and smaller, right? The terms are getting smaller and smaller. So the limit of that sequence as n goes to infinity is going to 0. But what about the sum? Now remember, the sum is we're adding up all of these terms. So what can we say about that sum? So if we look at this graph, right, this is S1, then S2 is the sum of the first 2 terms, sum of the first 3 terms, 4 terms, 5 terms, etc. We're adding these up. What happens? Well, it's inconclusive, okay? So if the limit of our sequence equals 0, then the conclusion about our series is inconclusive. We don't know what the sum of this series actually is, all right? So that's kind of the difference there. Let's move on to the next page and take a look at geometric series more closely. Okay, so a geometric series, what we can conclude is if our R value, the absolute value of it, is between 0 and 1, then we can go ahead and find the sum of this series, okay? We could go ahead and say it will converge, all right? So S is going to equal the sum of this sequence, A times R to the n. It's going to equal A over 1 minus R. So what does this mean? Again, it means that the series converges to A over 1 minus R. That's what this means. Only when the absolute value of R is between 0 and 1. So that example on the previous page, A, the example for A, R was 5/4. And we got that series to diverge because the limit of the sequence as n went to infinity was infinity. So overall that series diverged. But we were inconclusive in example B. But now we can make our conclusion. Okay, now our conclusion is, all right, since R was 1/4 in that example B, we could go ahead and find the sum of that series. It does in fact converge. We no longer have to say it's inconclusive. The proof for this is right here. Okay, you can certainly take a look at it and let me know if you have questions, but I'm gonna move on in terms of our video. So let's go ahead and talk about a few other things, okay? Now, Theorem 9.8 says the limit of the nth term of a convergent series. What does this mean? Well, using a series to determine whether a sequence converges. Now, before we talked about a sequence determining if the series converges or diverges, all right? If the series converges, then we can say the limit of the sequence is 0, okay? So we can say that. While the inverse is not necessarily true, a convergent sequence produce both convergent and divergent series. That's not necessarily true. But the contrapositive is always true, and that leads us to a very important test when we're getting into whether series converge or diverge. This is called the nth term test, all right? So highlight this, do whatever you need to do to know that this is a very important test, okay? So we would always start by taking the limit of our sequence. If it does not equal 0, then we can go ahead and say that the series diverges. So this is really just showing whether a series diverges. If the limit of that sequence equals 0, we're inconclusive, okay? This is only to show that a series diverges, all right? So for instance, if we have over here, our sequence is 1 over n, all right? And so our terms are 1, 1/2, 1/3, and that's this part here. But remember, the sum is adding up those terms. So it's going this route, all right? So if we have this, which the limit is going to 0, but then what does it mean about the sum? Well, we can see the sum continues to grow. So we can say that the sum is inconclusive. We don't know anything about the series yet, okay? So this only shows whether or not the series diverges. So let's look at the next page and practice some nth term test. Okay, so we're going to look at these 4 series, all right? And our first thing is we're going to try the nth term test, okay? And that's where we're going to leave it today, all right? So we're going to apply the nth term test. The nth term test tells us to take the limit of this sequence as n goes to infinity, okay? So looking at this first example here, we're going to apply the nth term test to see if this series diverges, okay? So we take the limit as n goes to infinity of that sequence, n over 2n plus 1. Well, we get an infinity over infinity with direct substitution, so we need to use L'Hopital's. All right, so taking the derivative of the numerator, taking the derivative of the denominator, we get this limit to equal 1/2. Our conclusion is that's not 0. Therefore, this series diverges. So this series diverges because the limit of that sequence doesn't equal 0. Okay? All right, let's take a look at the second one. Again, we're going to apply the nth term test. So we're going to take the limit as n goes to infinity of our sequence, 1 over n squared. We get 0. Therefore, it's inconclusive. We cannot make a judgment whether it converges or diverges. Later on, though, we're actually going to learn that it does, in fact, converge. Okay? But that's to come. Part C. Again, we're going to apply the nth term test. So we're going to take the limit of this sequence, 1 over n to the 1/2. When we plug infinity in, we get 0 again. Therefore, inconclusive. But guess what? Later on, we're going to learn that it actually diverges. So we're going to talk about the difference between those two. And then finally, our last one. Again, we're going to apply the nth term test. So as the limit as n goes to infinity of our sequence, e to the n over n. When we use substitution, we get infinity over infinity. So we have to use L'Hopital. Derivative of e to the n is e to the n. Derivative of n is 1. And so we get infinity. Well, infinity is not 0. So we can go ahead and conclude that this series, this entire series, diverges by the nth term test. All right, so you can kind of take a look at the sequence plot. So this is n versus an and what's going on. All right, okay, so you can see an, what's going on. It's getting bigger and bigger eventually. Okay, so it's going to diverge. Look here, and then look here. You can kind of make your conclusions there. The very last example, I know this has been a long video, is the bouncing ball problem. All right, so we're going to treat this kind of like a geometric series. Okay, so a ball 10 feet high bounces, rebounding to 4/5 of its previous height. Find the total distance the ball travels. So it is 10 feet tall, 10 feet high, it drops, it bounces, and it continues on. So we want to figure out, we want to add up all these distances forever and ever and ever, okay? All right, so initially we're thinking, okay, well, I dropped it. This is our 10 feet, and then the next time it was 10 times 4/5, right? And then the next time, 10 times 4/5 squared, 10 times 4/5 cubed, so on and so forth. But that's only considering the up part. We also have to remember the down part. So if I initially add 10 to this, okay, I'm thinking of this guy here then. So I'm initially thinking this entire distance, okay, is traveled 20. But if I add 10 to the beginning, I have to remember to subtract 10 in the end. So then each of these humps is really 4/5 of this original hump, okay? So that's kind of how we get this entire up and down portion of that bounce. So what we should notice then is my initial term is 20, plus 20 times 4/5 plus 20 times 4/5 squared, etc., and don't forget to subtract that 10 in the end. Well, this is a geometric sequence with A being 20 and R being 4/5. Well, 4/5 is the absolute value of that is between 0 and 1. So we can go ahead and find the sum of all of these terms, okay? Because it's a geometric series with A being 20 and R, the more important part, being between 0 and 1. So we know the sum of the series is A over 1 minus R, so 20 over 1 minus 4/5, and I can't forget to subtract that 10 at the end. Just cleaning everything up, we get this series, the sum of the geometric series, to be 100, but again, we have to subtract that 10. So we get the total distance traveled is 90 feet, okay? All right, when you get to class, we're gonna get lots of practice with all of these, so make sure you come with any questions.